Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at independent samples t-tests. So we've looked at dependent samples t-tests when each observation came in a pair. Now we're going to look at when the samples are independent. So you might have a control group and a group on which you perform an experiment. They might take a drug and you want to see if they get better. But there are different people in each group. You can't pair up the observations. So again, we're testing whether or not the means between these groups are equal. So we can have an equal variance or a separate variance t-test. You use the equal variance if the ratio of the sample variances is less than 3, and you use separate variance when the ratio is greater than 3. So in both cases, we calculate the standard error. It's a little harder to calculate the standard error in this case, but it's easier to calculate the degrees of freedom if it's an equal variance test. Calculating the degrees of freedom in separate variance is quite annoying. In both cases, our test statistic is t equals the sample mean difference minus our hypothesized difference over the standard error, this or this. And this is the formula for confidence intervals. All right, let's look at an example. So we're going to examine here, is there a significant difference in IQ between year 9 and year 10 students? So this is an independent samples t-test because year 9 students and year 10 are different. No one is in both. Now we can use this here because IQ is known to be normally distributed. So here I've generated some random statistics for each of our samples. So the first thing we need to do is determine which type of t-test we're going to use. We're going to look at the sample variance. Now here I've told you the standard deviation. Remember that the variance is just the square of that. So the variance for year 9, I'll call this s squared of 9, is going to be 16 squared 256. And the variance of year 10 is going to be 12 squared, which is 144. You can check that on your calculator. If you can't tell off the top of your head, this is clearly less than 3. We are going to use an equal variance t-test. The formula is here. So the first thing we're going to do is calculate this. This is called the pooled sample variance. So here, N1 refers to number in the first group, year 10s, N2 the number in the second group, year 9s. So N1 minus 1 is 31, multiply that by the variance of the first group, and then we plus N2 minus 1 by the variance of the second group. On the bottom is N1 plus N2 minus 2. So if we put that on our calculator, we get about 203.39. So we're using now this pooled sample variance to calculate the standard error. It goes here. So the standard error is the square root of this pooled sampled variance multiplied by 1 on N1, which was 32, plus 1 on N2, which was 36. So putting this in our calculator, we get about 3.46. That's the standard error, and we're going to use that to calculate the test statistic. So the test statistic is the difference in means. It doesn't matter which way around you write them. So here 104 minus 108 gives us -4. And we divide that by the standard error 3.46. So we get around about -1.16. That's our test statistic. Now the degrees of freedom are these two added up, subtract 2, so that will give us 66. So here we're going to use a two-tailed test because we want to know if this is larger than this or this is larger than this. We want to account for both possibilities. Now, if we're using the table, we have a bit of a problem because we want to use 66 degrees of freedom, but most tables don't have this. What we do is we round down the degrees of freedom because this is more conservative. So the closest number lower than 66 is 60. So if we put in T60 and we do it at the 0.05 level, we end up getting here about 2. So notice here that our test statistic is lower in absolute value than the critical t-value. And so in this case, we'd reject H0. There is no statistically significant difference in means. Clearly, there is a difference in the sample averages, but it's not significant. At the 95% confidence level, we can't say that the population means would be different for these two groups. All right, let's look at another example. So here again, we have two independent samples, and we'll test where there is a significant difference in means. So the null hypothesis, we'll call that the mean of year 10 and the mean of year 8s are the same. Our alternative hypothesis is that the means are different. This will be two-tailed because, again, we want to account for the possibility that 10s are greater than 8s or 8s are greater than 10s. So let's first determine which type of t-test we need to use. So here we have that the ratio of variances is 21 squared divided by 12 squared. That's greater than 3, so we're going to use a separate variance t-test. So in this separate variance t-test, calculating the standard error is actually easier. It's just the square root of variance of first group, so that's 12 squared divided by number in the first group plus variance of the second group, so that's 21 squared divided by number in the second group. So if we put that on our calculator, we get about 4.38. Now in the separate variance t-test, the annoying thing is calculating the degrees of freedom. So here for the degrees of freedom, the numerator will be 144 over 32. S2 squared is 441 again, and N2 is 30, and then we have to square that. That gives us the numerator. So we substitute basically the same numbers into the denominator. So if we put that in our calculator, we don't get a whole number. It's about 45.5, so we round up to 46. So here our test statistic is just the difference in sample means. That was 1. Doesn't matter which way around you write these. So it's just 1 over 4.38. So that gives us about 0.23. So we're going to compare this with a t-table. Again, it's going to be two-tailed. So again, if our table doesn't have 46 degrees of freedom, we round down to the nearest number that is on the table. So that's 40. 0.05 will be our level of significance. We get about 2.021. So we can see clearly that yet again our test statistic is lower in absolute value than the critical t-value. So we fail to reject the null hypothesis. So we conclude that there is no significant difference in means between year 10 and year 8 students. And of course, we expected that. The test statistic was very low. This is a very small effect size. It's unlikely that if we looked at the populations of year 10 and year 8, we would get a difference in means. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.